I'm Niels. I'm a materials engineer on the Reality Composer Pro team. Welcome to my session, Explore Materials in Reality Composer Pro. In this session, we're going to learn how to build materials for XROS using Reality Composer Pro. I'll begin with an overview of what materials are in XROS and describe how they customize the appearance of your 3D objects. I'll introduce the new material type available in XROS based on the MaterialX Open Standard. After that, I'll show you how to design materials using Reality Composer Pro's built-in editor called ShaderGraph. I'll take you through the process of creating reusable parts of materials using node graphs. And lastly, we'll build a geometry modifier for some great-looking 3D content. Let's first start by describing what we mean by material. Materials are what define the appearance of your objects in 3D scenes. Materials can be simple, just a single color, or they can use images. You might apply a wood texture to the model of a chair, or map an image of bricks to a wall. Materials can also be quite sophisticated. They might use animation to look like rippling water, or change appearance based on viewing angle. Think of the iridescent sparkle of mother of pearl. Materials can even modify the geometry of the objects they are applied to. Materials in XROS use physically based rendering, or PBR for short. This means artists can design the appearance of objects using physical properties similar to real-world objects. For example, how metallic or how rough an object looks. Let's look at some examples of physically based materials in action. Here's a sphere using a simple PBR material. This material uses a constant blue color with a reflectivity set to 40%. Or you might apply images to set color and surface roughness to get a convincing concrete. Or turn up the metalness and get something that looks like iron. You can even get something that looks like car paint. Materials consist of one or more shaders. These are programs that do the actual work of computing the appearance of their material. With RealityKit 2 for iOS and iPadOS, we introduced custom material. Shaders in custom material are hand-coded in metal. In XROS, we're introducing a new type of material called ShaderGraph material. This is the exclusive way of creating custom materials for XROS. ShaderGraph material uses networks, or graphs of functional blocks, which is where it gets its name. ShaderGraph material is based on an open standard called MaterialX, and is an artist-friendly way to define materials. MaterialX was originally created by Industrial Light & Magic in 2012. ShaderGraph material supports two main types of shaders, which we call physically based and custom. Physically based is a basic PBR shader. Choose this for simpler use cases. You configure this shader by providing constant, non-changing values, like colors or images, for each property. Custom shaders, on the other hand, give you precise and custom control over the appearance of your 3D objects. Custom shaders can incorporate animation, adjust your object's geometry, and create special effects on the surface of your object, like a sparkly paint look. You can build ShaderGraph materials using the ShaderGraph editor right inside Reality Composer Pro. Take a look at the ShaderGraph nodes below that instantaneously define the look of the terrain in the viewport. Now that we've understood the basics, let's build some custom materials. Materials in XROS can be created using Reality Composer Pro, a new pro developer tool that lets you compose, edit, and preview 3D content. If you'd like an introduction to the app before starting with materials, please watch the Meet Reality Composer Pro session to get yourself acquainted with the editor UI and its features. We'll use the Yosemite Valley model that was shown in that session and apply a topographical map appearance to it. I'll explain the math behind a material, then we'll go into Reality Composer Pro's shader editor and build it. There's a lot to cover. Let's jump right in. Here's the Yosemite Valley diorama Eric built in his session. To save on time, I hid all the objects we don't need for this session using the deactivate command. That leaves us with a pedestal in the middle and the landscape at the top. Pretty cool. Let's add a topography feature. We'll add a material showing the topography of our model by displaying contour lines along the slope of the terrain. It'll look similar to the topographical map that you might have come across when planning a hike. Let's create a custom material containing a shader that will draw contour lines on our terrain. We want to draw lines on our terrain through all the areas that have the same elevation, like in this diagram. This blue line, for example, shows all points on the terrain at 1,000 meters of elevation. Seen from above, it will look something like the diagram on the right. We're going to build up a material using a set of functions that will draw lines like these on our model. To start, click on the plus button at the bottom of our project in the Hierarchy panel. Under Materials, notice our two shader types, physically based and custom. Choose Custom. This reveals a shader graph of our editor. New custom shaders start with two nodes, the surface node in purple and the outputs node in blue. Your material's active surface is the one connected to the custom surface input of the outputs node. The inputs on the surface are how you set your shader's physically based, or PBR, parameters, base color for example. Let's give the material a descriptive name. Topography material sounds good. An important step is to assign our new material to our Yosemite Valley model. Select it in the project hierarchy. In the inspector, under Material Bindings, choose Topography Material from the Binding menu. Notice the model changes from color to a simple gray. Our material is working, but it doesn't do anything interesting yet. Let's fix that. Select Topography Material from the hierarchy to return to the shader graph editor. We'll connect some nodes to our surface inputs to draw stripes on our model in the right places. I'll illustrate how our material will work with this example terrain. We need our material to decide where to draw topographical lines based on its location on our model. So first, we'll add a position node to our material. This node returns our rendering position in 3D space. We're only interested in the height of position, so we'll also add a node called Separate to extract just the position's y-coordinate. Separate returns the y-coordinate of position, which increases with terrain height. Let's add these first two nodes to our material in Reality Composer Pro. Double-click on the background of the editor to add nodes. This brings up the new node picker. You can browse to the list of all the available nodes, or search for nodes by name or keyword. Let's type position and select the position node from the list to insert it into our shader. Position outputs the location in 3D space where the material is being rendered. Our material varies with height, so let's add a separate node to extract the y component of position. Double-click the background to bring up the new node picker again, and add a separate 3 node. To make connections in the editor, just click and drag from node outputs to node inputs, like this. These two nodes combined give us the height of the terrain. Next, we'll take the output of the separate node and pass it to a modulo node. Modulo gives the remainder of dividing two values. We'll use modulo to divide height by our desired topographical line spacing. The result looks like this. You can see height has been divided into bands. The height values inside each range start at 0 and increase to that range's height. This will be important for our next step. Let's add the modulo node to our material in Reality Composer Pro. Instead of double-clicking to add a node and then connecting it, we can drag a new connection to an empty space to create a node that's already connected in one step. In the new node picker, type modulo and click to insert a modulo node. Modulo has two inputs. The first is a dividend and the second is a divisor. You can conveniently set constant values on inputs in the inspector instead of connecting nodes. In the inspector, change the second argument to 0.1. This is the divisor and sets the width of our height ranges. We have just one more step to go before we can see our output. We'll use an if-greater node to determine where our repeating values fall in narrow height bands on our terrain. The if-greater node will return a value representing one of the two band colors you see on screen, depending on the result of a comparison. When the height is greater than our shader topographical line width, we'll choose a background color. And where the height falls within our desired line width, we'll choose our topography line color. Let's add the if-greater node to our material and see the results. We want to compare the result of the modulo node to a value we choose for our topographical line width. So I'll add an if-greater node to do that comparison. If-greater compares its two inputs and returns one value when its first input is greater than its second input, and a different value when the first input is less than its second input. This if-greater node is set to output floating point values, but we want to choose between two colors, one for our terrain and one for our topographical lines. In the inspector under Type, change this node to output RGB. Next, let's pick our two colors. In the inspector, I'll click on the color picker next to True Result and set our terrain color. Let's use white. Let's leave the false result, which is our topographical line color, set to black. This will give us a lot of contrast with our white terrain. I tried a bunch of values and arrived at 0.002 as a good value for line width, So in the inspector, I'll set my comparison value to 0.002. I'll connect the IfGrader node's output to our surface's diffuse color input. Awesome. Now our material is setting the color at every point on our terrain, and we've made a topographical lines material. Next, let's see how to use the node graphs feature. Node graphs help simplify complex materials and let you create your own nodes to reuse parts of graphs. We'll use node graphs to give a material a real topographical map look. Let's add a second set of lines between the current lines of our material. Here's what our material looks like so far, and here's what it will look like when we add our subdivisions. We'll start with the 4 nodes in our material that draw our topographical lines. Then we'll compose a node graph from them. This will combine our 4 nodes into a single node. Finally, we'll create an instance of our node graph to reuse its functionality. One node graph will draw our original set of lines, and the instance of it will draw our second set of lines. Let's go back into Reality Composer Pro and build it. Here is our topographical line shader again. Drag to select these 4 nodes that compute the colors for our lines and where to draw them. After selecting them, right-click and choose Compose Node Graph. Now the nodes appear as a single node that I can use inside other graphs. Let's assign a descriptive name to our new node. Let's call it Lines. We'll create a copy of this node graph to draw our second set of lines. For this, I'll create an instance using the Create Instance command in the hierarchy. Instances are live copies that adopt any changes made to the original node graph. We'll return to our material by selecting it. Let's call our new instance Secondary Lines. We want our node graph and its instance to draw lines with different spacings and colors, so we'll add 2 inputs called Spacing and Color to our original node graph to control these properties. Let's edit our original node graph by double-clicking it. You add inputs and outputs to your node graph in the inspector. First, let's add an input called Spacing and set its type to Float. We'll also add an input called Color to control our topography line color. Set the type of the input to Color 3. I'll connect these to the right places in our graph. Let's go back to our material by selecting it in the project hierarchy. Notice that our node graph now has the 2 inputs we created and that our instance inherited these 2 new inputs. On the original Lines node graph, set spacing to the values we chose before. And let's choose a smaller spacing and a lighter color for our instance node graph. The last step is to combine the outputs from our original and instance node graphs. I've conveniently chosen grayscale colors for both node graphs, so we can combine their colors using a multiply node. Nice! We have a convincing topographical lines material with 2 sets of lines. Next, let's talk about geometry modifiers. These are a feature of custom materials you can use to modify your models in real time. We'll replace our static terrain model and recreate it using geometry modifiers and height data. Then, we'll extend our geometry modifier to dynamically animate between 2 different terrains, Yosemite Valley and Catalina Island, California. When we're done, we'll have a dynamic terrain material that can animate between our 2 different locations. Let's see how this is done. All the shaders we've looked at so far are surface shaders. These are shaders that set the physically based, or PBR, attributes for each pixel of our model as it's rendered. Geometry modifiers are similar to surface shaders, but operate on the geometry of your objects instead. In fact, you build them right in the same editor in Reality Composer Pro. Let me give you an overview of the geometry modifier we're going to build that will create a terrain of Yosemite Valley using its height map data. We'll start with a flat disk model, which contains some plane geometry. This will be our base surface. Next, we'll use our terrain height data, which is 2D data about the height at each location of our model, and use a geometry modifier to raise the terrain by the correct amount. This will result in the terrain we want. Once I've shown the basic version, I'll demonstrate a version that takes 2 sets of terrain heights and uses those to animate between our 2 locations of interest, Yosemite Valley and Catalina Island. Here's another view. We'll start with a flat model, and our geometry modifier will move its vertices vertically using data from a 2D height map, like this. The first thing we'll do is use a deactivate command to hide the pre-built Yosemite Valley model. We'll generate the same Yosemite Valley model, but this time using our geometry modifier. I'll start with a flat disk model in my project browser. I can bring it in by dragging it into the root entity in the project hierarchy. I've gone ahead and created a new material named Dynamic Terrain Material and assigned it to the disk. Let's get to work on our geometry modifier. In the shader graph editor, we'll need a geometry modifier surface. We'll add this to our material alongside our PBR surface. I'll drag a connection from the custom geometry modifier input of our output node and choose Geometry Modifier from the new Node UI. Let's first apply our Yosemite Valley image to our surface. To read image data, we'll use an image node. In the inspector, let's assign our Yosemite Valley image to the image node's file name input. Things look a bit funny since the terrain is flat, but we're going to fix that now. We'll need the height data for our valley. It's in an image file which contains height values instead of color data. Since this data is in an image, we'll read it by adding another image node. Now assign our Yosemite Valley EXR image containing our height data to this new image node's file name input. Geometry modifiers can move the vertices of our model in any direction, but we're only interested in moving them vertically, so let's insert a combine 3 node to create a 3D vector with only the Y component set. Now, connect this to the geometry modifier surface's model position offset input, and boom, our flat model has been transformed into Yosemite Valley. There's one more step we need to take. When we move our vertices, we'll also need to set the surface normal vectors of our model to match our new terrain shape. There are ways to compute these from the height data, but today we're going to use an image that contains pre-computed normals for this geometry. Let's create another image node to read the normals. Since these are pre-computed, we'll connect them directly to our surface shader's normal input for better accuracy. Our surface expects normals to have values between -1 and 1, but the normals in our image are between 0 and 1. I've remapped the values from the image using a remap node. Now we've created the terrain from a flat geometry using height data. Next, let's make our diorama dynamic and add the ability to morph from one terrain to another. In this case, we'll add an animated transition to change Yosemite Valley to Catalina Island. To achieve this, we'll first add another set of image nodes to our existing geometry shader. The nodes contain the heights, colors, and normals for our Catalina Island terrain. Then we'll add mix nodes to blend between these two sets of heights, normals, and colors. Finally, we'll connect a value to our mix nodes to control blending between our two sets of data. Let's build this in Reality Composer Pro now. Okay, here's our material so far. Let's add another set of image nodes containing the same data, heights, colors, and normals, for Catalina Island instead of Yosemite Valley. Next, I'll add some mixed nodes to blend between our two colors, heights, and normals. Finally, let's connect a 0 to 1 constant to our mixed nodes, which will control which terrain is shown. You'll notice when I set my mixing constant to 1, the terrain shows Catalina Island. When I set the mixing constant to 0, we see Yosemite Valley. Now that we have a material that can transition between our two different terrains, let's make this transition progress value changeable from our Swift code. We'll use the promote command to convert our progress value into an input on our material. Inputs on materials become properties of your material that can be accessed from your Swift code. Now our material is ready to be used in our Diorama Swift app. Here's the final version, which combines our topography lines and our dynamic terrain. This version has some additional refinements, like anti-alias topography lines and ambient occlusion maps, all added using Shader Graph. Check those out in the sample for this session. So that's it. Today we got a brief overview of what materials are in XROS, designed a dynamic material using the Shader Graph editor in Reality Composer Pro, learned how to use node graphs to organize graphs and make your own reusable nodes, and finally, expanded on our knowledge to incorporate geometry modifiers to dynamically reshape our objects. Reality Composer Pro offers tremendous potential for designing materials, but there's a lot more to Reality Composer Pro and how it helps you create immersive experiences on XROS. In Amanda's session, Work with Reality Composer Pro content in Xcode, you will learn how to integrate Reality Composer Pro content into the Diorama Swift app. Also, if you haven't seen it already, check out Eric's session, Meet Reality Composer Pro, where you'll learn how to get started. I hope you have lots of fun exploring and designing content for XROS. Thanks for watching.